So this is on page 18 of your unit handout. The purpose here in this lesson is for us to solve trigonometric equations that you couldn't solve algebraically before, but you can now by using identities to turn them into trigonometric equations you could solve before. And I've talked about this before in high school math. Your job a lot of the time is to take a problem and use a little bit of knowledge that you learned at this level to turn it into a problem that you could have solved at an earlier level. And maybe even an earlier level and an earlier level. And we want to be able to find exact values and then approximate values if we require it. So when you take a look at, is that what the equation actually is? I don't think it is. Liam, help me out here. What should it be? Say again? Sine of 2x minus cos of x. And we could solve this one, but that's not, I know that's not what I wanted. Okay. So why can you not solve this trigonometric equation? That's correct now? You cannot solve it because when we're talking about, say, a reference angle, you've got cosines and sines. This is the big obstacle in this question. You've got a mixtures of sines and cosines. And by the way, you have 2x. And we really don't want to ever solve a trigonometric equation unless the argument on the trigonometric function, the argument being what you're taking the sine or the cosine or the tangent of, unless the argument is x or theta. 2x, algebraically, 2x is a mess. Because then you're not finding a reference angle for x, you're finding a reference angle for 2x, which doesn't really make a lot of sense. Okay? So what we're going to do is say I can replace the sine of 2x with 2 sine of x cos of x. And you might say to yourself, well, okay, but Mr. Way just said this is a mixture of sines and coses, and that's a problem. But it's not really a problem anymore, because this is something you could have solved and did solve. There's an exact practice problem that is this question by factoring out the cos x. So let's be clear here. I went from sine of 2x to 2 sine x cos x because that's an identity. It's in the double angle identity for sine, which I think most of you just know now. You go, oh, sine of 2x is that thing. So if I factor out a cosine of x, then we're left with 2 sine of x minus 1. And now we have 2 factors. And that means you can set each factor equal to 0. So, this is a Math 12 problem. A 30-1 problem. This is still technically here a 30-1 problem right in here, but as soon as we start writing stuff like cosine of x equals 0, which is kind of a 30-1 idea to go to this line, and 2 sine of x minus 1 equals 0, this is like a 20-1 problem. Forgot my 0. With certain limitations, but I'm going to go with a unit circle kind of approach here. When I talk about cosine, so I'm just going to put a big circle here and I'm going to use it for everything. When I talk about cosine of a rotation angle being equal to 0, cosine of a rotation angle equals to 0 at this location and this location. Right? We should know that. If you have to resort to a reference angle, I guess you could. You would take inverse cos of 0, get a reference angle of 90 degrees, and then start picking and choosing the appropriate quadrants. When you take a look at the second equation, which is 2 sine x minus 1 equals 0, When we solve that for the primary trigonometric ratio of sine x, we get 1/2. And you should know that sine of x is 1/2. Well, sine of x is the y-coordinate, and the y-coordinate of 1/2 is here. So these are the two locations where sine of x equals 1/2. Yeah, and if this is a written response, you're actually drawing this, I think. You can't just say, well, on the unit circle. I think you should draw it. What were we asked for a domain 0 to 2 pi? Well, it doesn't matter if it includes 0 or 2 pi. So this is something that I don't usually recommend because it gets very messy and cluttered. I don't recommend drawing the 4 rotation angles on there. This is where you might want to redraw them into 2 groups or even into 4 pieces. But this is theta equals pi over 6. This is theta equals 5 pi over 6. So this is going to get really ugly, right? This is pi over 2. And this is 3 pi over 2. I do not recommend what I just did here on a written response. Clutter and disorganization is not your friend when you're trying to get good marks. I mean, if I were marking it, I would go, yeah, they know what they're doing. I'd give you the marks. But you never know what the people in Edmonton are going to say. Those are your 4 solutions. Pi over 6, 5 pi over 6, pi over 2, 3 pi over 2. So what we did was we used an identity to change it from an equation that we couldn't solve to an equation we already knew how to solve. Any questions with that first example? All right, B, 2 cos x plus 1 minus sine squared x equals 3. So this is a classic example where you have a mixture of sines and cosines. And luckily, we can replace sines with cosines here. I want to try to make this point to you. To replace cos x somehow with sine x is never really an option, because there's no identity that connects those two things together. But there is an identity that connects cos squared and sine squared. And it's that 1 minus cos squared is the same as sine squared. So we're going to replace the sine squared with 1 minus cos squared. And of course, you're subtracting sine squared, and since sine squared is a binomial 1 minus cos squared, you need a set of brackets there. All we were doing here was just using an identity to replace sine squared with 1 minus cos squared. So what do we get? Let's clean this up a bit. We get 2 cos of x plus 1 minus 1. So this is how my mind works when I subtract something that is in brackets. I go minus 1, minus negative cos squared. I know some of you are taught, and it works for some of you. I just don't like it personally. It's not that it's a bad idea. Drop the brackets and switch all the signs. Put a negative 1 in front and multiply it through. There's lots of ways to do it. I now see that it's quadratic. So what I've done is I've turned it from a lesson 6.4 problem to, quite frankly, a problem from the previous unit. We learned how to solve these trigonometric equations in the previous unit. I don't know which section, 5 point something. It's quadratic, so I'm going to reorder the terms in descending degree order. And zero the equation at the same time. So 1 minus 1 is 0. I have a cos squared, I have 2 cos x, and then I have to zero the equation by subtracting 3. Let's see if this is factorable. The leading coefficient is 1 on the quadratic term. So if it's factorable, we would be after two numbers that multiply to give negative 3 and add to give positive 2. That's easy enough. That would be easy enough, and then I'm positive 3 and negative 1. Yeah. I need to see them on paper just to confirm. Are we okay with that? I hope. Good. So now we're definitely in the realm of a simpler problem. Cos of x can never be negative 3. Cosine of x always has a value between negative 1 and 1. Think back to the graph of y equals cosine of x. It oscillates between negative 1 and 1. Think about the value of x on the unit circle, because on the unit circle x is the cosine of the rotation angle. X always goes from 1 to negative 1 and back to 1. It never goes outside of that. I'll call it a range of values. Where is cosine of x equal to 1? Well, if you look at the unit circle, there's only one location where cosine of x is equal to 1, and it's right there. That's it. That's the only place on the unit circle where x is 1. Go ahead, Evan.
Because the domain for the question says 0 is less than or equal to theta, which is less than or equal to 2 pi, technically there's two angles that work.
Yes. So that's what I was just about to do. I like the approach of identifying the locations first. So I, in my head, was already thinking ahead like that. But what I'm saying to you when I draw this diagram is I'm not giving you an angle yet. I'm just saying, here's the place. Now, you're right, Evan. We look at the domain. And the domain, I guess it says the domain in the previous page. It says 0 to 2 pi, and this is a rare case. Normally we either include 0 or 2 pi, but not both. Here we can have 0 or 2 pi. So Evan is exactly right. The solution here will be that x is equal to 0 radians and 2 pi radians because of the equals to part of the inequality symbol on 0 and 2 pi. There's a less than or equal to, less than or equal to. Any questions with that example? All right, let's try another one. Number 2. I believe there's a problem with your number 2. And it's that I think I give the equation in terms of x, and then I told you the domain in terms of theta. Is that right? No? Are they both in terms of x? Okay, must be another one I'm thinking of. So we want to solve this. Well, holy smokes. We got sines, we got cosines, we got tangents. I'm just going to ask the question. How many of you see that tangent of x times cosine of x is sine of x? What we would do here is we would replace tan of x with sine of x over cos of x we would replace sine of x with 1 over cos of x, or sine over, let me start again. We would replace tan of x with sine of x over cos of x. The cosine of x's cancel, and we are left with sine squared of x equals 1/2 sine of x. So it is quadratic. We're going to zero the equation. But also with an equation, we don't have to work with fractions if we don't want to. We can multiply both sides of the equation by 2 in this case to get 2 sine squared of x equals 1 sine of x. And now we can zero the equation. I need to look at something. Give me a second. So now where we're at is we are at 2 sine squared of x minus sine of x. It's quadratic. We can factor it. I know there's a lot to remember in life and in math and in this course. But when you have a quadratic equation that's missing the constant term, there's a quadratic term, there's a quadratic term, and there's a linear term, but there's no constant term. Then you factor out the greatest common factor, and there will always be one. I'm left with 2 sine x minus 1. Well, we're back to familiar territory. Sine of x equals 0 for the first factor, and sine of x equals 1 over 2 for the second factor. Because on a written response, you'd write 2 sine of x minus 1 equals 0. You'd rearrange for sine of x. So on the unit circle, and I'm forcing you to use the unit circle idea here. And as I said, you write your exam or diploma exam, use your coffee cup to draw a circle. The nicer the circle you can draw, the easier things are to imagine and see. Where is sine of x equal to 0? Sine of x is equal to 0 here and here. Where is sine of x equal to 1/2? Here and here. So those are the locations. Now what are we after? Zero to 360, including 0 but not 360. So we will have 0 degrees for this one. We will have 30 degrees for this one. We will have 150 degrees for the third one, and we will have 180 degrees for the final one. Okay. We need to check something, and if I didn't check it, we would still get the right answer. But because there is a cos of x in the denominator of the original equation, there are non-permissible values. Cosine of x would never be allowed to be 0. So prior to me canceling that, you would say cos of x cannot be 0, and you would say, okay, where is cosine of x 0? Because those places are not answers. They can't be answers. And cosine is 0 here, nope, here and here. So those two positions are not allowed for this equation. The non-permissible values, in other words, are x cannot be pi over 2 plus multiples of pi, where n is an element of the integer number set. Okay. So what we need to do is look at our answers and see if any of the answers are these, because if some of the answers we put in our list are these non-permissible values, we need to strike them from the list. Did you have a question, Sienna? Can you repeat that, please?
Can't you just substitute tan of x, cos of x with just sine of x?
And ignore the non-permissible values?
Well, because I was thinking because tan equals sine of the cosine, and if you rearrange it, then it would just equal sine of x.
And yes, and that's what we really did here. I just showed it in steps. So yeah, you and I are on the same page, because I just think, well, tan times cos is sine. Be careful, though. I think you need to show this on an exam if it's written response. Absolutely, I'm with you. I go, well, tan times cos is sine, obviously. But what's obvious to us might not be obvious to it's obvious to a marker, but the marker wants to know that you know why. Okay? So these two positions are not allowed. They're non-permissible values. or lead to non-permissible values. Were any of our answers those two positions? No. So these answers are all legit. But if we went through this process and we ended up with 90 degrees, you'd have to cross it off and say it's non-permissible. Number 3. Julie, help me out in a loud, clear voice. What does number 3 say?
The example number 3.
Yeah.
Solve
Cos 2 theta? Gotcha. Are we looking for a general solution in radians? Thank you. I don't know why that's not there. Okay, well, we got to get rid of that double angle. So I want you to go to your formula sheet and take a look at the double angle identity for cosine. And there's 3 of them. Right? We can change the cos of 2 theta. I see everybody's looking at your formula sheet. We can change cos of 2 theta to cos squared theta minus sine squared theta. That could be a thing we could try. We could change cos 2 theta to 1 minus 2 sine squared theta. Is that right? We could try that. Or we could change it to 2 cos squared theta minus 1. I'll tell you right now, any of those 3 options will eventually get us there, but one will get us to our destination a lot quicker. Which of the 3 should we use? Jason?
The 2 cos squared a minus 1.
Excellent. So I'm going to write 2 cos squared theta minus 1 equals cos theta. And why is that? I think it's obvious, but other people might not know why it's obvious. Why are we choosing that one? Right. We don't want to mix things up and get cosines and sines. So what Jason said is it's the only one without sine. It's the one that has exclusively cosines. And the number 1. And now we say, well, it's quadratic. And we're back into the previous unit where we have 2 cos squared theta minus 1 cos theta minus 1 equals 0. And we're going to factor this. By the way, I have never seen, nor do I Yes? So what I'm doing here is when I zero a quadratic equation, I have to move everything to one side. I prefer to have the quadratic term, which is the cos squared term, as positive. So the following 2 terms are already on the left-hand side. Oh, yeah, and I did that because in a bit I'm going to stress that we have to factor that and we need 1 cos theta that's negative. I have never seen, nor do I ever expect to see in my career, a trigonometric equation that's quadratic that's not factorable in Math 30. Math 31, calculus? Yeah, sure, why not? You'd have to use the quadratic formula. So this would be 2 cos theta. Cos theta. It's got to be 1 and 1. And by playing around with the numbers a bit, you can see that if you have the negative 1 over here with the cos theta, your outer product will be negative 2 cos theta. Your inner will be positive 1 cos theta. Which adds to give negative 1 cos theta, which is what we have here. That's the reason I put the 1 there, as I just wanted to stress that it's negative 1 of them. Are we okay with the factoring? So I've been a little lazy here in some of these. I've been writing stuff like cos of theta equals negative 1/2. Again, I want to emphasize to you that on an exam, my exam or the government exam, I would want to see that statement on a written response. And it's negative 1/2 anyway. And the other one, we know cos of theta equals 1. But you would have to write cosine of theta minus 1 equals 0. All right, what are we talking about here? On the unit circle, cosine written response, I'd probably go unit circle. Again, you guys don't, on a written response, you're not saying stuff like, I subtracted 1 from both sides and divided by 2. That's algebra. You're showing that work with mathematical language. You don't need to describe in words how you're rearranging something. But here you might want to say on the unit circle, the cosine of an angle is the x-coordinate. So if this is -1, this is -1/2, we're dealing with this position and this position. For that, where is cosine equal to 1? Only in this position. So what are your solutions? And we wanted a general solution. Well, this can be described by saying multiples of 2 pi. I don't think we need to say 0 plus multiples of 2 pi. Multiples of 2 pi does it. The one in quadrant 2 can be described as saying 2 pi over 3. Here's 1 pi over 3. Here's a second pi over 3 plus multiples of 2 pi. The one in quadrant 3 can be described by saying 4 pi over 3. There's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, plus multiples of 2 pi, where n is an element of the integer. And that's fine. That's an acceptable answer. But there's another way to write that answer. And I think you're likely to see this on the diploma exam. You could say, I'm going to redraw that circle so that it might be easier for you to see this. You could say instead, if it is this position, and this position, you could say that theta is equal to 2 pi over 3 plus, could just say this. Multiples of 2 pi over 3. And the reason is, when you look at these three angles, or these three positions, they are all 2 pi over 3 away from each other. And I've actually seen questions, everybody, that give you this picture, a multiple choice question, and says 4 students, Alice, Betty, Charles, and Danny, A, B, C, and D, whatever they're called, have all done this, and they've correctly indicated that those are the locations. Here's what Alice says is the answer. Here's what Betty says is the answer. Here's what Charles says. Here's what Danny says. Who's right? Maybe Alice and Danny are both right because Alice said this and Danny said what's on the left. Capiche? You understand? Any questions? All right, we have one last example to do. 3 cos x plus 2 equals 5 secant of x. Well, I hope it's obvious. It might not be. That I think our first line of attack here is to get rid of the secant and replace it with cosine. I think it's a very wise move once you do that to multiply both sides of the equation by cosine of x because we don't ever want to work with fractions. And I get 3 cos squared x plus 2 cos x, so I'm multiplying this through, equals 5. Because the cosine x's cancel on the right-hand side. So it's quadratic in cosine of x. I'm going to, when I say quadratic in cosine, that means cosine is the thing that's being squared. I'm going to zero the equation. And now we're back in more familiar territory. We're going to have to factor this. I'm going to do the trick that I taught you in 20-1 and we've talked about here. Let's just confirm that it's factorable by figuring out b squared minus 4ac. If that's a perfect square, then it's factorable. And I believe it's 64. Good. And 64 is a perfect square. So it's factorable. And again, I believe these quadratics will always be factorable. But this is just a confirmation. I don't want to try to be factoring something if it's not factorable. I mean, it's got to be 3 cos x and cos x, and to multiply to give 3 cos squared. The 5 has to come about by multiplying the 2 integer parts of the binomials, which is going to be 5 and 1. Even the thought of putting 5 here tells me I'm on the wrong track because my outer is going to be a whopping 15 cos x's, and I only want to end up with 2. So the 5 is going to go here. The 1 will go here. My inner is 5 cos x. My outer is 3 cos x. So what do I need? I need positive 2. That means the 5 has to be positive and the 3 has to be negative. So where did the 3 come from? It came from the 1 times the 3 cos. So this has to be minus, this has to be plus. Sometimes the solution is kind of a letdown because the first factor is going to be cos x equals negative 5/3. The first factor will lead you to that conclusion. The second factor leads us to this conclusion. And cosine of x is equal to 1 here. Right? Yes? Where is cosine of x equal to negative 5/3? Well, it isn't ever equal to negative 5/3 because negative 5/3 is outside of the range of cosine of x. Cosine of x as a graph has a range from negative 1 to 1. Negative 5/3 is negative 1 point, excuse me, 3 repeating or 6 repeating, I think. So that's why I say it's kind of a letdown. Now, just a second though. I mean, we could say, are we after a general solution? So 2 pi n would do it. Are we after it in radians? So x equals 2 pi n. I apologize if somewhere in this lesson I was using theta instead of x. And I think there was a question, 3 or 4, where I had theta in the domain and it was x in the equation. If that's the case, just assume they're the same thing. I'm not saying that's okay. I'm saying they need to be the same thing, and that's a mistake on my part. But this equation had, and you look at non-permissible values before you cancel, it had cosine of x in the denominator, which means cosine of x would never be allowed to be 0. Where is cosine 0? At the top of the unit circle and the bottom of the unit circle. So this is saying x cannot be pi over 2 plus multiples of pi. Is this location in one of those non-permissible locations? No. So our answer is right. I want to go back and check something because I just want to make sure this is what I wrote for the other one. For some reason, I think I wrote something different. And I just want to make sure about that. That was the one with the tangent. No, I wrote the correct thing. I thought in my head, I wrote plus multiples of pi over 2. So that's what you're doing in this section of the course is you're taking an equation and you're using identities to rewrite the equation in a form that you can work with. So there are some textbook questions. Okay? On page 25, there are some equations that would involve you using the sum and difference identities. And number 4b is, I call it dirty. I think it's a great question, but I think it's such a trick question that on an exam nobody would get it. If you want to challenge yourself, that's great. On page 29, question number 2 deals with some equations where you're going to almost exclusively be using double angle identities. And 2i and 2j are really tricky, I think, anyway. I would start with the textbook. Some of the ones in the handout are a lot more complicated. So that's it. We're going to get going on review tomorrow. You have about 20 to 25 minutes here. Well, about 20 minutes. And yeah, about 20 minutes.